going to look at the different definitions of solutions. Solution chemistry uses many different combinations of units to report the concentrations of dissolved substances. The following list of techniques provides a useful repertoire for any chemist. First of all, let's look at what we mean by a solution. A solution means that you have a solute dissolved into a solvent. In the case of high school chemistry, we're usually talking about water as a solvent, although it can also happen that you have things like methanol or ethanol or some other liquid that is more suitable to dissolving whatever it is you're trying to solubilize. Concentration is a concept where we describe how much of a substance, a solute, is dissolved in the solution, into the solvent. And the solution is what is made up of both the solute and the solvent together. So when you mix the solvent with the solute, you get what's called a solution. Concentration can be reported using the mole. The mole, as the chemist does it, is 6.02 times 10 to the 23 of anything. For chemistry, it is defined as the number of atoms in 12 grams of isotopically pure carbon-12. Now, three definitions using the mole are commonly used. The first one is molarity. It's probably the most popular one. It is the number of moles of solute per liter of solution. And here's the key idea. Per liter of solution, which means the combination of the solvent and the solute together is what constitutes the solution. And it's measured in units of moles per liter of solution, I should say. There's also something called molality, which is the number of moles of solute per kilogram of solvent. That would be useful when you have a process that might have temperature differences, and the result of temperature difference will cause a difference in the volume of a solution, which would cause an apparent change in concentration. So to overcome that limitation, chemists have developed the concept of molality, which is based on kilograms of solvent. It has units of moles per kilogram of solvent, not of solution, of solvent. Finally, we have mole fraction, the number of moles of solute per moles of solution. Again, moles of solution being the total number of moles of two things mixed. If you're mixing two liquids, for example, you could have moles of water and moles of methanol, and the total moles is what's on the denominator. Weight fraction is another thing that's popularly used. It means the number of grams of solute per gram of solution. Now, of course, it can vary. You might sometimes get per 100 grams of solution, or even per 1,000 grams of solution, or even million grams of solution. If you get per million grams of solution, we call it parts per million. If it's per thousands of grams of solution, we call it parts per thousand. We can get solutions that are as low in concentration as part per billion for certain types of chemicals that might have environmental impacts. We can go as low as the part per billion level to monitor their presence. For example, if you were monitoring for the presence of plutonium in drinking water, God forbid, then you'd want to do that at the part per billion level because plutonium is an extremely toxic substance. Weight per volume fraction is the number of grams of solute per ml of solution, and can also be per kilogram or other variants of volume. And finally, you have weight percent, where it is the number of grams of solute per gram of solution, and then multiply by 100 to turn into a percentage. The first three definitions are used more by chemists, and the last three can be seen in industry, where you don't necessarily have trained chemists doing the procedures, although even that, you can have both things happening. My personal experience was that molarity was not used that much outside of the classroom. Now, to get you used to the idea of working with the mole, I just framed the question that is to help you understand how big the number 6.02 times 10 to the 23 is. The question asks, if the Earth is 150 million kilometers from the sun, if a piece of cardboard is 1 millimeter thick, how many moles of these paper sheets would you need to make a stack, to make a pile tall enough to reach the sun? So the distance to the sun is 150 million kilometers. We're going to turn that into meters by multiplying by 1,000. That helps us to cancel the kilometers. And then we're going to multiply it again by 1,000, turn it into millimeters. That'll tell us how many millimeters the distance is from the Earth to the sun. Well, if one piece of paper is 1 millimeter thick, it'll also be the same as the number of papers. And the number of moles, number of sheets in 1 mole is 6.02 times 10 to the 23. So your number would be 2.49 times 10 to the minus 10. So 2.49 10 billionths of a mole. So even though we've given ourselves this seemingly impossible task to make a pile of paper all the way to the sun, it still ends up being a tiny fraction of 1 mole. So it is a very large number, and what we're dealing with is very tiny things, atoms. So we need very large numbers to make macroscopic quantities of something that is that small. The next question is a very simple molarity calculation. If you have 0.1 mole of sugar, let's say in this case glucose, and it's dissolved into 1 liter of, it's dissolved into 1 liter of solution, or I should say even better, is dissolved into enough water, I want to say this accurately, enough water to form 1 liter of solution. What is the concentration? Okay, this may not seem like a very important point, and when the amount is that small, it probably wouldn't make a very big or noticeable difference. But there is a difference between 1 liter of water and 1 liter of solution. The difference being the presence of the sugar. Sometimes when you add sugar to the water will increase in volume ever so slightly, and that has an effect on the final volume. So that's why we distinguish between liter of water and liter of solution. So that solution means the water after sugar has been added to it. So the volume of the solution is measured after the sugar is all mixed in. And that's how you calculate the concentration. So to begin with, we'll find out how many moles we have. Well, we were told it was 0.1 moles, and it was 1 liter of solution. So the concentration is moles of solute divided by liters of solution. It comes out to 1.1 moles per liter. Another way of stating that is to write a capital M, 0.1 M. And the way we would read that is 0.1 molar. So it's a 0.1 molar concentration. And the next question we ask, if 0.1 moles of glucose is dissolved in enough water to make 0.5 liters of solution, what's the concentration? Here's the glucose concentration. And notice I put a square bracket around the symbol for glucose. Square bracket means concentration in chemical terms. And we have 0.1 mole of glucose dissolved in 0.5 liters of solution. 0.1 divided by 0.5 gives you 0.2. So now we see we have double the concentration from the previous problem because we have half as much of the solvent. Now we make it a little bit harder. The question asks, a chemist mixes 50 grams of sugar into 1 liter of water, which weighs 1,000 grams. Let's assume that's 1 liter, okay, of volume. Let's assume that the temperature is such that the final volume of the solution is 1 liter. And that way we can use the definition using it. Let's first find out how many moles of sugar we have. 50 grams of glucose divided by the molar mass of glucose, which is composed of 6 times carbon, 12 times hydrogen, and 6 times oxygen, gives you 50 divided by 180. You have 0.27 moles of glucose dissolved in 1 liter of solution. Here's the definition for molarity. Moles of solute divided by liters of solution. 0.277, this number here, divided by the number of liters of solution, gives you the same number of molarity. We only had 2 significant figures here. We'll assume this is an exact number. So this is 0.28 molar. That is the concentration. Now we'll increase it a little more in difficulty. 1 sugar cube, which we'll assume weighs 2.2 grams, is dissolved in an Olympic swimming pool with dimensions of 2 meters by 25 meters by 25 meters, full of water. Now, table sugar is sucrose, which is C12H22O11. What is the sucrose concentration in the pool? Note well that 1 liter of H2O, we'll assume in this case, is 1,000 centimeters cubed. And you can also say 1 meter cubed is equal to 1,000 liters for the sake of this problem. The first step is to find out how many moles of sugar we have. 2.2 grams of sucrose, which is C12H22O11, divided by the molar mass of sucrose, otherwise known as table sugar. Gives you 6.4 times 10 to the minus 3 moles of sucrose. The volume of the pool in meters is 2 by 25 by 25, which is 625 times 2, or 1,250. Then we multiply by 1,000 liters per meter cubed. The meter cubes cancel, and we end up with 1.25 times 10 to the 6 liters of water. 1.25 million liters of water are in that Olympic swimming pool. And we'll assume that the addition of 2.2 grams of sugar is going to have a negligible effect on the volume of the solution. We'll assume the solution still has a volume of 1.25 times 10 to the 6. Here's the number of moles of sucrose. Number of moles of solute divided the volume of the solution gives you the following number, 5.14 times 10 to the minus 9 molar. And then what I did is I converted to a more easily handleable measurement. I multiplied by 1 billion nanomolar per 1 molar, and that gives us 5.14 nanomolar concentration. Nano means billionth. You see that 10 to the minus 9 is a billionth. Okay? And that's how to calculate molarity.